Okay, so I'm going to talk about now the Raoult's law and Henry's law. They go by side. And like I said before, the Raoult's law is working when you are dealing with A became the major component. And the beauty of the Raoult's law is still the property of the gas phases can be expressed by the property of the liquid phase. And this even the PA star is a term that has a physical meaningful term. What's happening when you are in the pure component, that's the vapor pressure. Raoult's law is kind of borrowing the idea. I want to know the vapor pressure of the solute, which is a minor component. And should be proportional to how much you have of a solute in the solution and the proportional term that called KB. And what I'm going to do is because I want to put it in a one form, and I want to highlight the Henry's law this time. So let me draw this diagram one more time. This time, let's draw this way. So this time I'm going to use the XB. Okay, and this is a 0. This is just my choice for choosing an x-axis. Now this time is a mole fraction of B. So this is a case where you have a B is a solute. Right? And this is a case where now B is solvent. Right? Depending on where you are, this side is where you are in the solute. This side is B is a solvent. And then this is a pressure. Then I'm interested in what is a vapor pressure when you are 100% B? This should be PB star. All right? Okay. And what's my vapor pressure when you are here? You should be 0. Okay? You have nothing, so therefore no vapor. And like I said, if life is simple, everything at the same levels of interaction before and after, they should follow this Raoult's law line. Right? And then I mentioned that do not pay attention to the A or B. I just say when the component is solvent, which is when in here, not A but B, your B is your solvent, they should behave like Raoult's law. Right? So that's where the region that Raoult's law works. Maybe 100% down to 99%. Maybe you're pushing your luck if you're 95% or something like that. So that's the one that is true. And then you start to say Raoult's law fails miserably, right? But eventually you have destination it has to be 0. So it's that's the sort of the more realistic picture in real cases. So this once again, this region, I can happily say vapor pressure of major component, which is a solvent, and XB, PB star, right? So that's the Raoult's law. What about the Henry's law? Henry's law is they only care about what is a minor component. So this is a region that we're Henry's law, and looks like there is another equation that is governing it. Right? So this is a region that I can say looks like vapor pressure PB proportional to XB. But the slope is not defined by a pure property, but somewhere way down up there. Okay? The slope here, so what we call the KB. So if you go to this one all the way to the top, there will be way up there somewhere here is a KB. If I make this one more realistic then. Move it like this, and if I draw this, line up there, there will be my KB value, which is nothing to do with anything, just one of the parameters that you have to figure out by doing experiment. So this equation, I just want to know, I mean, nobody can predict this, okay? This is, you're dreaming that it is not going to be predictable, but in the limit of when your B is a minor component, I can use a proportional constant as a Henry's law constant. When B is your major component, I can use a pure vapor pressure of that component. And I can using this two little circular lines, and this is where Henry's law works. This is where the Raoult's law works. Somewhere in between, you are out of law. You cannot do it. But still, it is a very important game here. And one thing that what people do is, this is a conceptually useful. Well, what people also do is PB is actually, they use a symbol different one. DB. So this is actually what is actually working. So what I did is I just changed my mole fraction into, this is a molality of B, which is your solute. So for example, partial pressure of CO2, okay, is a molarity of a CO2 in water times Kb CO2, which is a Henry's constant, in water, let's say 25 degrees C. So this is one thing that you should know, that the meaning of Henry's constant, although this equation seems to be very misleadingly simple, it's just borrowing what we learned from the Raoult's law and the chemical composition dependence to be a linear term, not the square term. If you're there to kind of predict this kind of curvature term here, you need a non-linear, right? Something complex function. And this is something that probably more complicated business that beyond this lecture, even for any graduate course lecture, somebody's PhD thesis, they only can solve the handfuls. So I like to give it, the practical use is Henry's law, so I like to put an example. What is CO2 solubility? In water at 25 degrees C. I mean, this is a very important question that I would like to know, and the PChem course is telling me that, okay, CO2 solubility in water. The skill that you need to learn is, water is my solvent. This is my solute. And they want to know the solubility. So the solubility can be expressed in terms of molarity of CO2 or mole fraction of CO2. You guys can choose whichever equation the information is given. Okay? And then what you can see now is Kb is 3.01 times 3. Look at this unit, kilopascal per mole. So this is an example of Henry's law constant for CO2 in water, and that's a unit. You see that what this is related to? It is related to the pressure, vapor pressure of a CO2 with their molarity concentration. So therefore, this one is actually, I'm going to use PB is BB times KB. And then the problem, this problem is the textbook problem saying that, okay, the PB, vapor pressure is, let's say, 10 kilopascal or something. Oh, 0.1 atmosphere pressure. So they give you this information. What is, essentially they give you the vapor pressure of the CO2, and then so therefore you can predict what's the solubility of CO2 in water, knowing that I can look at the table. This is a table, what's the number? You got that? Yeah, it's in the table. It's in the textbook table. Okay? If you look at the Raoult's law, Henry's law table, it's showing these numbers. So you pull out these numbers and you can calculate this. And the answer for this PB is actually 3.4 10 to the minus 3 mole per kilograms of water. So this one is so small, okay? The solubility of the gas is so small. Molarity is something that is easier they want to tabulate and do the experiment because they don't want to deal with the total solution volume that you guys used to do. So this is a way that many of people tabulate essentially their values of Henry's law constant to describe the gas solubility in terms of this unit. Okay? So it just actually comes down to this factor that what is a unit for the Henry's law constant, which is a pressure, vapor pressure divided by molarity of your gas solute. And this is what. One thing to let you know, right? The partial vapor pressure is something that sometimes we can measure that because there are sensors that are just sensitive to the CO2 gas. Or sometimes all you gotta do is you measure the total vapor pressure. That's easy to measure by pressure gauge. And then you essentially measure what's happening in the gas phase, the mole fraction of B, and by doing it you can calculate this. And the chemical composition of this one can be probably done by gas chromatography or some other kind of mass spec technique that you can calculate. So knowing that I was able to measure the vapor pressure or the chemical composition in the vapor phase to back calculate my vapor pressure, partial pressure of your gas, and using the Henry's law constant, you can calculate gas solubility.